The Monty Hall Problem. A famous probability game show puzzle made famous by Monty Hall, host of the game show Let's Make a Deal. Humans have found an optimal solution to it, but does AI come up with the same solution? Let's find out. So in this video, we will be covering the following topics. What is the Monty Hall Problem? LLM GPTs understanding and solution to it. Coding the Monty Hall Problem in Python. And lastly, training a reinforcement learning agent to solve the Monty Hall Problem. Firstly, what is the Monty Hall Problem? Imagine you are on a game show and presented with 3 doors. Behind one door lies the prize, which is a car, and behind the other 2 doors lies goats, which are not prizes. You are required to pick a door, and you will get whatever is behind the door. After you have made your choice and before the door of your choice is revealed, the host, who knows what is behind each door, opens one of the other doors which you did not choose. It reveals a goat. You are then presented with a choice to either stick with your original choice, or to switch to the other unopened door. Which would you choose? Intuitively, it might seem like it doesn't matter whether you stay with your initial choice or to switch, as there are 2 doors left, and each should have a 50% probability of having the car right. However, the key to it is to understand that the game show host, Monty Hall, has knowledge that you don't. He knows which door has the car and which doors have the goats. When he opens one of the other 2 doors, he's not randomly selecting a door. He's deliberately showing you a goat. With this information, the probability of the car being behind each door changes. When you first choose a door, there's a 1/3 chance that the car is behind that door and a 2/3 chance that the car is behind one of the other 2 doors. When Monty Hall opens one of the other 2 doors and shows you a goat, the probability that the car is behind your original door remains 1/3, but the probability that the car is behind the other unopened door is now 2/3. So in order to maximize your chances of winning the car, you should switch doors. By switching doors, you merge the 2/3 probability of the car being behind one of the other 2 doors into a single door, giving you now a 2/3 chance of winning the car. If you stick with your original door, you'll only have a 1/3 chance of winning. Scratching your head and trying to make sense of it? Don't worry, you are not alone. This is definitely not very intuitive. But before we dive into coding, let's ask the LLM GPTs what they think. I have enlisted the help of 3 GPTs, which are ChatGPT, Google Gemini, and Meta AI, to help with this problem. I started by prompting them for their understanding of the Monty Hall problem and what the solution would be. I have only displayed ChatGPT's answer, but they all gave the same textbook answer, which, well, is to be expected as they have been trained on databases provided by human input. Now, let us prompt them with the Monty Hall problem. I have used the same word prompt of imagine you're on a game show and given a choice of 3 doors. Behind one door is a car, which is the prize. And behind the other 2 doors are goats, which are not prizes. Which door would you pick? With a subsequent follow-up prompt of before your choice door is revealed, the host opens another door, door 2, which reveals a goat. You are then given a choice to stick with your original pick or switch to the other unopened door. What would you do and why, if necessary, for all 3 GPTs and tried it 5 times? Here are the results. As expected, they are all able to produce the same answer, which is to switch doors all the time. And, as long as the GPT randomizes the initial door choice, the percentage of success is 60%, which is close to the expected probability of the solution. Interestingly, ChatGPT always sticks to door 1 as its initial choice. Now, what if we change the context of the problem but we retain the spirit of the Monty Hall problem? Will they still be able to provide the same answer? That's what I did, and they still provided the same answer. Seems like they are able to contextualize problems and apply the same solution to it. Now, let's get started with Python coding. We will be using Google Colab as usual, and I will share the link in the description box below. As always, we will first import the libraries which we will be using. We will need NumPy and random to create the Monty Hall problem, and Matplotlib for plotting the metric chart of our reinforcement learning agent. We will also need to pip install the gymnasium library to set up our custom reinforcement learning environment. Next, we will define a function for the Monty Hall problem. This is going to be for us humans to visualize the problem in code first before we transpose it to a custom environment suitable for reinforcement learning. We are going to create 3 subfunctions within it for clearer visualization of what takes place. The first subfunction is going to be for the first step, where the player chooses one out of 3 doors initially. First, we will define 2 lists here, with values 0, 1, and 2 in it. This will act as our door selections. Why do we need 2 lists here? We will see this further down below. The values within the lists can also be chosen to be 1, 2, and 3 for easier clarity of door numbering. It is entirely up to you. We will print out a message stating the problem and your choices available. Then, we will create a while loop, and within it, we expect the player to return an input which will only be exited after the conditions are met. Else it will not continue to the next step. The first thing inside the while loop is to have a user input box. We will also put in some exception handling here in case the player doesn't input the expected values. The exceptions which are caught here are when the player inputs string values or numbers which are not 0, 1, or 2. Once the player has provided a valid input, we will randomize the selection of the door with the prize, and remove the initial user selected door from the list choices _2. This list would be reduced to 1 element, which would be used as the open door or the door to be switched to for the user depending on the situation. For the next few lines, they are an if-else statement for choosing the door to be opened by the host. If the prize-winning door is not chosen by the user initially, it means that the prize-winning door is one of the 2 doors left and the host will open the other door. However, if the prize-winning door has been chosen by the user, the remaining 2 doors don't matter and the open door is randomly selected. After exiting the loop, it will also output a list of variables, which we will feed as inputs into the second subfunction called second choice. The user will be presented with an option to either stick with the initial door or to switch doors. At this stage, the list choices _2 will only contain 1 element, and the value of it depends on either of the 2 situations just mentioned. Similar to the first function, there is going to be a while loop and it will only be exited after the player provides the appropriate input. There is the same exception catching here as well. Once again, when the player has provided the appropriate response, the loop will break and output the new response as the variable final selection, which we will then feed into the third subfunction called check. The check subfunction assesses if the chosen door is the prize-winning door and will output the results accordingly. The last few steps are just to connect the subfunctions with the correct inputs and outputs to ensure that it runs correctly. I have included a commented out line of code for a visual inspection of the interim values just to see how it works as well. And that's all for the problem. Let's test it out below. Great, it seems to be working as expected. Now, we can put the optimal solution to the test. We will code out another function for the Monty Hall solution, and remove all the human inputs. We will pass in a parameter called rounds for the number of times we want to run this. As the solution is to always switch doors, the initial choice doesn't matter and we will randomize it, similar to what we have done for the prize-winning door. We will then hard-code it to always switch doors, followed by recording the results of the optimal solution in a results list and return the list as output. Let's run it 100 times. We can see that the success rate is pretty close to the 67% as per the solution. How about 1,000 times? The results show the same as well. You can run this several times and you will find that the results are pretty close. Now, let us move on to training a reinforcement learning agent. As there are no Monty Hall problem environments in the gymnasium library, let us code a custom environment for it. We are going to create a Monty Hall class and inherit the properties from the gymnasium.env object. We will define only 3 subfunctions here for it to work, as we do not need to visualize it. The three subfunctions are the init self method, step, and reset. Within the init self method, we will initialize the environment parameters, such as the action and observation spaces, state, and other parameters. Next comes the most important part, which is the step function. Here, we have taken the same approach to coding the prior Monty Hall problem and followed the same steps here. We will randomize the initial door choice similar to what we have done with the solution, and the only action the agent has to choose is to either retain the initial door choice or to switch. We will log the details of each episode in the info logging as well. Lastly, we will reset the environment parameters each time the reset function is called. After the custom environment is built, we will also need to register it in the gym registry before we can call it for usage. Now that we have completed building the custom environment, we can test it out here. Great, it's working as well. We will then move on to the last part of building the reinforcement learning agent. Since it is not a particularly complicated scenario with only 2 actions to choose from within a single time step, let's go with a simple Q learning agent. We will define a small Q table with some parameters for learning and update it at the end of each episode. We will also allow it some leeway for exploration at the start before it switches to the greedy approach. We will record the actions and results of it and will use it to plot a chart later on. Now that we are done with it, we can do a test run to check that it is working as expected. Excellent, we can proceed to train it for 10,000 episodes. After the training is completed, we can plot a chart to see what strategy the agent employed towards the end of its training. Perhaps unsurprisingly, we can see that over time, it has actually gradually shifted to favoring switching doors as the number of episodes increased, although there are some times that it chose to retain the initial choice as well. But the change in the action population over the episodes show that the RL agent has determined that the best strategy to obtain the reward is to switch doors. We can also verify the success rate with the strategy, and it is still quite close to the estimated probability rate calculated from the provided solution as well. So it seems that all roads lead to Rome, and indeed the optimal strategy for the Monty Hall problem is to switch doors, despite how unintuitive it is. We have confirmed the probability by checking with AI LLM GPTs, running the experiment over a large number of times using the optimal strategy, and training a reinforcement learning agent to solve it. All of them came up with the same optimal strategy. It might seem a bit anticlimactic and unsurprising at the end, but the probability speaks for itself and it is what it is. At the very least, we have verified that the solution does work out statistically. And that's the end of the video. Do you have any thoughts on it? Feel free to comment in the comment box down below. If you liked this video and would like to see more content of this nature, please be sure to like and subscribe as well. Thanks for watching, and until next time.